Throughout this year of calculus, we've learned about a variety of theorems, but never have we learned about the person who came up with the theorem. So today I'll be talking about the history of L'Hopital, the man behind the theorem, and then we'll talk about the theorem itself. Thank you. L'Hopital came from a long line of French noblemen, so from a young age he had access to acclaimed education. He was offered a variety of subjects from Latin to English, but he was really drawn to mathematics. And at the age of 15, he had the opportunity to meet with a duke, and the duke offered him this impossible math problem. And a few days later, L'Hopital returned with the correct answer, proving himself as a mathematical prodigy. L'Hopital, like his many male relatives, served in the military. That means that he had to put his passion for mathematics on hold. Or so he thought initially. But he actually spent most of his time in the army in his tent studying volumes of geometry. And so that when he finished his military service, he still had his math ability. In 1691, L'Hopital had the amazing opportunity to meet with Johann Bernoulli, a famous mathematician. And because L'Hopital was a member of this mathematics circle in France, he was able to hear a few lectures that Bernoulli offered. But that wasn't enough for L'Hopital. He was so moved by Bernoulli's teaching of mathematics that he sought him out and hired him to give him private lessons. He even helped L'Hopital draft his many works, and this relationship with the mathematician is what many historians credit L'Hopital for his rise to fame in the world of mathematics. In 1695, L'Hopital published the first ever textbook about differential calculus. In his introduction, he recognized the foundation of calculus that Newton, Leibniz, and even Bernoulli made, and he also added his own ideas. In fact, it wasn't until chapter 9 when he mentioned his famous L'Hopital's rule, the one that he's most remembered for today. L'Hopital contributed so much more to the world of mathematics than just his rule. He was a mathematical prodigy and a go-getter. But most importantly, he was known for his personality. He was humble and kind when mathematicians of the time were typically arrogant. In fact, Julian Coolidge, an American mathematician, described L'Hopital as an inspiration, stating that he was a shining example of a man of the highest social distinction whose love of learning drove him to devote much of his short life to scientific writing. L'Hopital is an inspiration for math students everywhere.
Now, we will be proving L'Hopital's rule. As many of y'all already know, L'Hopital's rule states that for the limit of f of x over g of x as x approaches b, b can either be a constant or infinity. If the limit of f of x as x approaches b and the limit of g of x as x approaches b both equal 0, or if both parts equal infinity or negative infinity, then the limit of f of x over g of x is equal to f prime of x over g prime of x. A common misconception is to use the quotient rule in this scenario, but no, you just take the derivative of f of x and the derivative of g of x. In order to prove L'Hopital's rule, we can use a Taylor series, which is a BC concept. We'll go more in depth about it next year, where it's basically an approximation of a real function using an infinite series. So we can use the Taylor series for f of a plus h and g of a plus h, which are just expanded versions of f of x and g of x. We can use the Taylor series, which are f of a plus h equals f of a plus h of f prime of a, and g of a plus h equals g of a plus h of g prime of a, to solve and then prove L'Hopital's rule. Thus, since we're using Taylor series and we're using it in terms of h, we can rearrange f of a over g of a in terms of the limit as h approaches 0, so we can rewrite it as f of a plus h over g of a plus h. Thus, we can use the nifty Taylor series that was already presented to reformat what our limit looks like. So we expand it into f of a plus h of f prime of a over g of a plus h of g prime of a. And since f of a equals g of a and both of them equal 0, since we're proving this in terms of 0 over 0, then the limit of f of a plus h over g of a plus h can be rearranged to just include h of f prime of a over h of g prime of a, and the h's can cancel out, so we have the proof of L'Hopital's rule as f prime of a over g prime of a. However, we must use a different proof in order to prove L'Hopital's rule in the case of infinity over infinity. So basically, we can rearrange f of a over g of a if it approaches infinity over infinity, as 1 over g of a over 1 over f of a, which would then approach 0 over 0, since 1 over infinity is approximately 0 when we're using limits. Thus, we can apply L'Hopital's rule to 1 over g of a over 1 over f of a in order to test to see if L'Hopital's rule applies to the overall form. So when we apply L'Hopital's rule, we then would use the chain and the power rule of differentiation to have the latter function be transformed into negative g prime of a over g of a squared all over negative f prime of a over f of a squared. And then we can use basic algebra to rearrange that into negative g prime of a times f of a squared over negative f prime of a times g of a squared. Then we can use cross multiplication and we can use algebra to cancel out the different negatives and other variables to then get f prime of a over g prime of a. Thus, L'Hopital's rule does apply when the limit approaches infinity over infinity.